And we're continuing on with our discussion of circular motion. And we were talking about Newton's universal law of gravitation on Wednesday. We were calculating accelerations due to gravity at places other than the surface of the Earth, where we know it to be 9.8 meters per second squared. Now we've moved on to talking, and at the very end of Wednesday's work, we talked about orbital motion, and now today we're specifically talking about that and the work of Johannes Kepler, many decades, centuries ago, looking at the solar system and the objects up in the sky, and making some conclusions, drawing in Newton's second law with accelerations and like that, centripetal accelerations. And you should have stumbled on three laws in the pre-lecture video last night. Kepler has. We can only really work in this class with one of them. One of them is a factoid. You just know or you don't know. It might be handy in a Trivial Pursuit game to know about orbits of planets around a sun or satellites around the Earth, perhaps. And then there's one that's talks about how fast objects move as they move around in orbit. And we can't do much with that because we don't know enough about angular momentum, and it's a kind of a calculus-based argument. But there is one that specifically relates how long it takes for an object to go around in its orbit to how far away it is in its orbit from the center of mass of the thing that it's going around. So that's what we're talking about. By the way, it's an important prerequisite if you plan to go on and take perhaps one of the astronomy courses, even some of the environmental science courses that are taught. The material from Wednesday and today is a prerequisite. One of the things physicists always believe in is, we really are kind of an order-based discipline. You just can't walk into an astronomy course if you haven't had PHY101 or some equivalent. Okay, it's not like other disciplines where you could take any course in any order. Astronomy kind of has to follow this, and hopefully you saw that. I do have one slide I want to share with you at the start. Oh, one other thing. I mentioned the pre-lecture videos. I have noticed, and I should probably confess to you that I have the ability to see in Canvas who's watching them. Okay, so I get kind of a gross number of how many people out of the class are watching them. And if I dig down even deeper, Canvas will tell me each and every person that watches the pre-lecture video. And, I was kind of happy when I was getting about 2/3 of the people watching it. That's, in this business, that's success. I have noticed a drop off, and that may be because it's the midterm and you've got a lot of other work that you're doing, papers, things like that for other courses. But I would urge you to watch the pre-lecture videos before you come to class. I think you'll get a whole lot more out of it, as well as reading. And by reading, I often mean scanning the book before you come in, as opposed to coming in just cold and have me do polling questions with you, and then we work problems. There's some effectiveness to that, but I think it'll be amplified if you do watch the pre-lecture videos. And I recognize there's about 1/3 of the people that are just not going to do that, and that's fine. But I did see a big drop off. The thing that prodded me to go look at that is yesterday's lab, and for some of you, Wednesday's lab, obviously centered around what we did in lesson 5.4, chapter 5, the 4th lesson with the pulleys. And I went to see how many people watched the video, and it was around 1/3 of the people had watched it. And I'm not sure how accurate Canvas is, but I would recommend it. If those of you that used to do it, it was around 2/3, and now we're dropped down to about 1/3. I would recommend you get back into it. Hey, I want to share this screen with you. Let's see, sharing PowerPoint. And I would have loved to put it in the pre-lecture video. It's just too darn big to fit. I think you're seeing it. Yeah, I see a green border. Yep, I do. And what we're showing here, obviously on the left, is the Earth. And am I recording? Let's just make sure I'm recording here. Yep, I am recording. The Earth is sitting right here, and there's these zones where various satellites are in orbit. And the first one it's called LEO, Low Earth Orbital Zone. And that's where a lot of the action's taking place. That's where the International Space Station is. That's where Mir used to be, I guess. I don't know if it's still up there. Hubble's up there. A lot of communication satellites are sitting in this region right here, right near the Earth. And then there's this kind of open area where not a lot of satellites are located. And then we're in this mid or medium Earth orbit region, and GPS is sitting out here. Okay. And part of the reason GPS is out there is it just needs to be in all the places that we want it to be. And so it's just a handy place to be high enough to cover large swaths of the earth with an individual satellite that's up at that height. Okay. And then if you go even further out, you see this thing we talked about. And I did an example problem. You'll see another one in the homework next week. And so if you can't do the geosynchronous orbit problem in the homework next week, go to the pre-lecture video for today, because I pretty much solved the problem. Anyway, way out here, where we go from the medium to the high Earth orbit zone, that's where geosynchronous satellites are. And they're very important because geosynchronous means they have a period of exactly 24 hours. So once they're set at a place on the equator, they stay there. Okay, they just rotate around the Earth at exactly the same rate at which the Earth is rotating. And so if they're sitting right over, I don't know, some place in the middle of the Atlantic Ocean, they stay at that point. And they're handy for communication because if you have the ability to bounce a signal off a satellite and then go to another receiver, you know right where to aim your transmitter, because you know where the satellite is. It's always in the same place relative to where you are. And I should tell you, we use those in the Navy all the time for various communication channels back to our home base. And so, very important thing. Some of the GPS satellites are up there. You may have heard of Iridium. It's the satellite telephone network that's very expensive, but people do use it so that they can literally speak on a telephone from anywhere in the globe. A lot of those satellites are up there, and very useful place. Space is a pretty packed business around the Earth. If you saw the movie Gravity with, let's see, who was in Gravity? I just had her name. Anyway, great movie. I think they do a pretty good job of letting you know what satellites are up there, how you can move around. I recommend the movie. It's a fun movie to watch, and it discusses what's going on up in space. All right, hey, that's it. Any questions before I get started with the polling question? All right, interesting stuff. I recommend astronomy. I've actually never taken an astronomy course in my life, sort of self-taught in that regard, but interesting discipline. And Professor Kem, Dr. Kem, who some of you have for lab, he is by research area, by profession, our resident astronomer. Okay, he also does environmental science work, obviously, but he is an astronomer. So if you're interested in taking a course, talk to him about it. And here's the first polling question. I'll let you read that. No questions from out there. Where are my polls? There it is. They always move the logo thing around on me. The little icon moves. And there it is. Which of the following isn't one of Kepler's laws? By the way, while you're thinking about it, I'll tell you all three of the laws, all four of the statements are true. Okay. So that isn't going to be the thing that delineates which is the right answer and which is the wrong answer. It's more of a categorization sort of question. Yeah. And I think most of you see it. All right. I got two more people I'm waiting on, but I think we've been about a minute on a straightforward question. So I'm going to end the poll and share the results with you. And I agree with the majority here, the 12 of you who picked C. A is true. Planetary orbits are elliptical with the sun at a focus. No proof of that. It's just a factoid. If you're ever playing Trivial Pursuit, you get a science and nature category. I don't do people even play Trivial Pursuit anymore? Any event, any trivia game, yeah, it's true. Planets are in orbit. Most of them are not very eccentric. If you're a mathematician, you know that means kind of stretched out ellipses. Most of the orbits are close to circular, which is a special case of an ellipse. But the center object in the case of planets, the sun, in the case of a satellite going around the Earth, like the moon or any of these communication satellites we're talking about, the center planet has to be at one of the ellipse focus points. Okay. Line connecting the sun to a planet sweeps out equal area in each equal time. Absolutely true. In this class, being an algebra-based class instead of a calculus-based class, I can't prove that to you. But if you think about it, in an ellipse, when the object is closer to the sun, say, which we call perigee or perihelion. Para is Greek for near. Okay, when it's closer to the object, it must be moving faster than when it's further away. And I have a picture where I'll show you that in a bit. But it is true. You can accept it as a factoid right now. A line connecting the sun to a planet sweeps out equal areas in equal times, and so that means when it's closer, it must to the thing it's going around. It must be moving faster than when it's further out. C is true, but that's Newton's universal law of gravitation. It's not one of Kepler's laws, and that's why it's the right answer. And then D is the thing that we are focusing on in this lesson, and that's Kepler's third law. And everybody's going to be working once we finish talking here about Kepler's third law and do some polling. We're going to be doing a third law problem, and it essentially says that the square of the period is proportional to the cube of the radius if you are using a circular orbit. If you're using an elliptical orbit, because a circle isn't a good enough approximation for what the orbiting body is doing, well, then according to Kepler, it was the semi-major axis. Major axis is the long axis of an ellipse. Half of that, so it's like a diameter. Half of that would be the semi-major axis, and it's equivalent for us to the radius. Okay, and that's what we've got. Average distance cubed, that radius cubed is proportional to the period squared. All true. Stop sharing that. I'll move on to the next one. And based on what I just said, I guess, hopefully this is an obvious answer. I guess you have to know a little bit about geometry of an ellipse, though. Interesting. All right, waiting on two people again. Maybe internet issues.
Dr. Tukolsky?
Yeah.
I'm doing Zoom on my phone, and it's not going to let me answer this
Okay,
question.
gotcha. So I won't wait for you. Thank you.
Yeah.
Thank you. Good to know. So there may be somebody else in the same boat. Okay, so we'll end right here after 23. All right. Hey, it's one of those things, and this is something I've long believed about teaching physics, and that is sometimes, what you bring into the course affects how you can move on. As I said, we're kind of an order specific discipline. If you don't know anything about ellipses because a high school geometry teacher never even mentioned it with you, well, then when I talk about Kepler's laws, it's a little bit lost. I thought most people have done this, though. The answer is B, and I'll share the results with you just so you can see what I'm talking about in terms of disappointment here on my part. That's the center of the ellipse. Ellipse is the focus. One would be right there, obviously, in A, and the other one would be about there. And if you've ever done this, it might be a kind of fun thing to do. Take a piece of string that's a given length and put a pen right there, and then move the string all the way around. Okay, that is the definition of an ellipse. Okay, if you've never done this, literally take two thumbtacks and a piece of string on a piece of paper on like a corkboard or something, and draw the shape that results when you stretch the string out all the way around 360 degrees. That will be the shape. So focuses are here, foci probably, following the Latin, I guess, are right there and there, and the sun would be at one of them. Okay, this is not a focus. That's just the center of the ellipse, and that's not where the focuses are located. By the way, that thing I talked about, the semi-major axis, would be that direction. Okay, that's the long direction on an ellipse. And the short direction here is called the, I'm sorry, that would be the major axis. The short direction is the minor axis. Those are like diameters. And so this distance right here, I think in the video last night, I call it S. That would be the semi-major axis, which approximates a radius, right? It's the closest thing we got to a radius. And oh yeah, this region over here, that's what we call perihelion, Greek near, or perigee. And if there's an area being swept out right there, and there's an area being swept out right there, and according to the second law, they have to be equal. You can see that that kind of means it has to travel that distance in the same amount of time as it travels that distance over there. So it must be going a whole lot faster when it's at perigee or perihelion than the other side, which is called aphelion or apogee. Okay. And that's Kepler's second law in a nutshell, I guess. I hope I didn't, no, I didn't ruin my next question. Any questions about ellipses? Yeah, and so the reason people get this wrong isn't because I didn't just tell you that, first law of Kepler is that the center body there, either the Earth or the sun, whatever the thing that the satellites are going around has to be at one of the focus points. It's because mathematically nobody's ever told you where the focus of an ellipse is, and other than last night's video, by the way. So that's something I would urge you. I recognize that, and so that's why it was in the video. I'll stop sharing this with you. We'll move on to the last one.
Dr.
Yeah,
Tukolsky,
go ahead.
how is C an example of a ellipse
Yeah,
then?
good question. And C would be the special case when, okay, so how do you transition from here to here being legal? What happens when when the focuses of an ellipse, okay, when they become closer and closer together, okay, so that's a pretty eccentric ellipse is what the mathematicians would say. That one's a little less. That one's a little even less eccentric. And what's happening is the two focuses are coming together as it gets less and less eccentric. And when it's a perfect circle, the two focuses come right on top of each other. And that is the special case. A circle geometrically is a special case of an ellipse. And it's the special case when the two focuses are sitting right on top of each other. Okay, so that's why C is a good answer. And by the way, C is the one that we're gonna do in our class. It's not the right answer because even the moon is in a slightly elliptical orbit around the Earth, but it's close enough to being a circle. And we all know the formulas for circles, like the circumference is 2 pi r. So in a class like this, that's as good as we get. We assume everything is in a circular orbit. I should tell you, if you're a physics major, you take an advanced mechanics class in your third or fourth year, and they look at something called elliptical coordinates, where you can solve the problem with more accuracy because you can actually assume that the orbiting body is an ellipse. And by the way, we'd never gotten to the moon if we'd assumed things were in circular orbits, right? Because that's just not true. And so this is the kind of stuff that what was it? The NASA folks have been doing, and it was a great movie that just came out, Hidden Figures. That's what those ladies in those offices were doing calculations on for NASA before computers, and then those ladies became the people who initially worked with the computers in order to do calculations of the moon's orbit and how we're going to get from the Earth to the moon in those days. But in our class, C is going to be the best answer. And is my explanation of how an ellipse becomes a circle okay? It is just a special case when the two focuses come together. All right, let's move on to, did I share that? I guess maybe I did. Stop sharing. And we'll go to the last question. And this is the material of today. Launch it. Which planet of the three there, and they're all pretty eccentric. Well, 2 is pretty circular, isn't it? But 1 and 3 are pretty eccentric ellipses. All right. 23 should be everybody, and I think you got it. And that's good, because this is, some of the other things we talked about today are general information, but this is what you have to take away from today's lecture, okay? The period squared is proportional. That's what that symbol that looks like a fish, I guess, means, to the radius, or as Kepler said, that semi-major axis. Oops, that's supposed to be a 3 cubed, okay? And how did that come about? What is the constant that relates those two? Well, what we did is we said, all right, let's see. I can, I guess, figure out from M at the center. Well, let's go mass of the satellite, mass of, in this case, the sun, and I guess I shouldn't use S for both. Let's go planet. Okay, one of the 3 planets that's sitting here, times G. Let's see, divided by R squared. Okay, and I'll even go capital R, since that's what I put in Kepler's law. That has to be the only force in each case here, which is pulling the planet towards the sun, right? There is no other force. There's no tension. There's no normal force. There's nothing like that. That's why this is gravity is such a fascinating force. It works over a distance without any contact, right? In any event, that has to be equal to the mass of the planet times the acceleration of the planet, which is, of course, centripetal. Okay, and so cancel. Oops, nope, that doesn't cancel. Sorry. I meant to cancel that one and one of those. The planet mass cancels, and you can see here that the velocity, which I meant to not cancel there, but now I will, square root of G times the mass of whatever that thing in the center is. In this case, it's the sun, right? Divided by how far away you are. And so we're talking about that distance R right there. And it is center to center, to be clear. And sometimes that matters, because sometimes for those low Earth orbital satellites, the altitude is just a small fraction of what the Earth's radius is. So you better add the Earth's radius to go center to center. On the other hand, when you're way out in the high Earth orbital, where the geosynchronous satellites are, you were several times the radius of the Earth, but it's still always center to center. In any event, what Kepler did, though, is he looked at that speed and he compared it to the circumference of the circle, because again, we don't have an equation for what the circumference of an ellipse is. So this is as good as we can do in PHY 101, divided by the period. Okay, and you can see right away, you got a radius there and a radius there, and you got a period there, and those are mathematically related. And so it's just a matter of pushing on this result and figuring out what the constant proportionality is. And it's on your equation sheet. Okay, and you will always be given this Kepler's third law. But as you saw in the video, there's a lot of constants and a lot of units, right? G, Newton, meter squared per kilogram squared. You got a mass, so you're gonna have kilograms, and you're gonna have some radiuses and some seconds, and you got to make sure all your units come out right to whatever it is you're trying to find. If it's period, you're trying to find it in seconds, and if it's radius, you're trying to find it in meters. Okay, so that's the lesson of today, I guess. And I did a couple examples last night in the video. If this doesn't make sense, check it out. I want to shift over from the PowerPoint to just show you what's on today's worksheet, and start sharing that. If I can find where Zoom managed to put, yep, there it is. And Adobe Acrobat, there it is. And what I put on today's worksheet, I'm moving it, so okay, hopefully you're seeing. I gave you the astronomical data, which are some of the numbers you'll need to put into Kepler's law, right? Mass of the sun, for example, how far the Earth is from the sun. You can see those numbers, and hopefully the exponents are clear and readable for you when you go to look this up. This table is in the back cover of your textbook. In the electronic version, it's at the very back in something called, I think, back matter. So if you ever need it, they're available. Probably a quicker way to do it might just be to go to Google. If you need a distance from the Earth to the sun, or from the Earth to the moon, or something like that, Google it. But this stuff is sitting on the back. There's your equations with the right constant. Okay, that's a big one. And there's your velocity equations that I said we're just going to use. And I'm a little bit schizophrenic in that I use lowercase r sometimes for radius. I like lowercase r because it reminds me center to center. Uppercase R is usually a particular radius, like the radius of the Earth, if something is going on at the Earth. But as long as you're clear and you're consistent in which one you use, you can get away using both. Okay. Any questions? All right, so I got 3 problems then for you, and we'll break up here. And they're fairly short. I think in about 10 minutes, you should be able to finish them up. So my hope is that we can come back and somebody's willing to show their solution to the rest of the class. And that way you don't have to upload it into Canvas. Here's the first one. I want you to use Kepler's third law that the period squared is proportional to the radius cubed. And I want you to find, using the chart up there, what the period of the Earth is in seconds. Okay, and so apparently you're going to need some masses like the sun and the distance to the Earth. Plug it into Kepler's law, figure out what the period of the Earth is in seconds. And of course, you should know that's 1 year, so you can check this. And then the second thing I want you to do is to use one of these equations then to figure out what the speed is, right? And you got your choice here. You can either use 2 pi r over the period once you've got the period, or you can use Newton's universal law of gravitation times the mass over the radius. And I think each group is going to have that option. Okay, these 3 are over specified. The 3 equations that I've got sitting here, they're more than you need. Any 2 of the 3 will answer the questions. That's one of the things I like about physics. You don't have to memorize every equation. You just have to know that they're out there and you manipulate them. And if you can do the algebra, you're in good shape. All right, here's the next one, that GPS satellite. This one you want to be careful about. And I throw this out for everybody. Notice I'm giving you the height of the GPS satellite above the surface of the Earth. And so what I talked about when you're getting the radius, remember the radius, let me draw you a picture here. There's the Earth. There's the GPS satellite. This number right here is this distance. Sometimes people will call that the altitude. Okay. And remember, when we're using Kepler's law or the Newton's universal law of gravitation, we want little r. That's why I kind of like it sometimes. Okay. And of course, there's the radius of the Earth right there. And so from a picture, little r that you'll use to solve this problem is equal to the radius of the Earth plus whatever the height above the surface of the Earth is. And that's often why people will get this problem wrong. They'll just put the 20 kilometers, even if you convert to meters correctly, okay, you forget to add on the radius of the Earth because each of the laws that we've studied the last 2 days, Newton's universal law of gravitation or Kepler's law, deals with center to center distances, okay, to your satellite right there. There's your GPS satellite. Okay, so that's one for everybody, even the people not doing this problem. When you see it on an exam or one of the homework problems, that's what you got to remember to do. All right, and then here's the last problem. The satellite is twice the Earth's radius. Again, you have the same correction, right? H here is exactly equal to the Earth's radius. And so you want to figure out what the speed of the satellite is and the orbital period. All right, so we'll divide up here real quick. I'm going to go 9 groups. And let me erase all my markings here, which are causing me not to be able to see my screen. All right, groups 1, 2, and 3, you're doing problem 1. That's Bridget, Shanice, Stephanie, Cora, Ellen, Emma, Andrea, Katie, and Rachel. Doing problem 2, Allison, Olivia, Sean, Chenyi, Elena, Michael, Maddie, Megan, and Sydney. And then doing problem 3, Jaleel, Tommy, I'll get it right eventually, Anna, Kristen, Jackie, and Nina. Hey, have fun. We'll see you in a little bit. I'll be jumping around rooms to help you work these problems. All right, any questions on what you guys are doing?
I don't have any.
Okay, yeah, I think it's pretty straightforward, and hopefully you've got all the numbers you need to crunch it. And I would just compare your numbers before you leave, and we come on back.
Thank you.
All right.
Oh, there he is.
He's here.
Yep,
Yeah.
here.
Is screen sharing enabling, because we're trying to share the document, but it's not working.
You have it enabled, yes.
Do you want to try again, Jackie?
Okay. Yeah, it says the host disabled participant screen sharing.
All right, well, let me look again. I did it in security on the center meeting. I enabled screen sharing. See what I gotta do.
I can't do it just because I'm on my phone.
Yeah, understand.
I'm trying to see if I can share like a whiteboard, but I don't know how to describe to Jackie how to share the whiteboard or how to do the whiteboard because
Well,
I'm
you
not
go to
on
the green button, right? And the green button opens up a pop-up, and then
Oh, look, I can write on it.
Can you write on it now?
Yeah, you saw.
All right. That I opened that up, which I'm still surprised because I've never had that problem before. My other class, they just open it up, even if I've authorized them to screen share. Once you're in groups, you can open it up. All right. Anyway, you able to see this whiteboard here now?
Yeah.
Yeah, but once you leave, it's going to go away.
Yeah. So I would do is what some groups do is make a screenshot of it before you leave.
Oh, great idea. And then I
Yeah.
can just do it on my phone.
Yeah, exactly. Especially on your phone, you can just do whatever you hold the button down and it saves it for you. All right.
Yeah. Will you unshare so I can share it?
I don't know what you mean. If I stop sharing, it's going to go away, I think.
But I screenshotted it so I can put mine up. So
Oh,
when you
okay.
leave, it doesn't go away.
All right.
Let's see.
I'll stop sharing.
Okay, hold on. Photos. Done. Oh, you're in it. Can you see it?
I see it. It's kind of small, but yeah, it's there.
Can you see it when I zoom in?
Yep, you're zooming in. Okay. All right. Can you write on it though? That's really the question.
Yeah, look.
Oh, look at that. You're in business.
Jackie, do you know how to write on this?
There's under view options, pull down view options. Near the
Okay.
bottom it says annotate, and then you
Okay.
write with your mouse or a finger.
Okay, got it.
All right, so to get started, let me see. What is the speed of the satellite? So we have to go to this chart. Dr. Tukolsky.
Yeah.
To get started on this, do we need to reference the chart?
I think you're going to need it because if I'm right, I think you got to get speed, right?
Yeah.
And so speed is the square root of g times, in this case, the mass of the Earth, which you're going to have to get from the chart, and then divided by the radius. And so you're going to, and they're told that the radius is 2 Earth radii. So this will be twice the radius of the Earth. So you're going to have to go to the chart for that as well, right? So yeah, the two numbers you'll get from the chart are those two guys. And then of course I gave you that constant. It's right below the chart. And then take the square root, and that should get you speed.
Okay.
Thank you.
All right. This is fair. This is what I think a lot of people want physics to be. You find the equation, you plug the numbers in, make the units work out right, and see if the number makes sense. All right.
Okay, so our G is 6.67384 times 10 to the negative 11.
Yeah, and you probably only need like 3 or 4 of those digits.
I know.
I usually just do 6.67 for most, and you're close enough. All right, I'll leave you guys alone. I'm going to another group.
Thanks.
You bet.
And then our mass of the Earth is 5.9.
Hi guys, any questions?
Yeah, I have a question.
Sure.
So like the first thing I did the third law equation to find t, to find the, but I got a different number than what the period said like on the data chart.
Okay.
And
do you have anything you can share to show, or you want me to look at a whiteboard here? What number did you get?
I got 5,000.
For the period?
Yeah, for t.
Okay, so here's what I think can you see my whiteboard right now?
Yeah.
Okay, so this is why it's a fairly, I mean, it is just a simple equation that you're plugging numbers into, but the numbers are complicated numbers, right? They're all exponents and they've got units and you're cubing things. And so you got four. One of the mistakes I make all the time is I forget to square that pi right there. Okay. And then you've got G, which is this big long number. And then you've got, what mass did you use? Would you put it right there?
The 5.98.
Yeah. Okay. So here's what I think. Remember, that's the sun and the earth. The mass you should be using is the mass of the thing at the center. So it's the mass of the sun.
Oh, okay. Yeah, that's why I went wrong then.
That makes sense. It's all this
Yeah.
mass right here is always the thing at the center. And then of course,
Okay.
all right.
And then, okay.
Yeah.
Thank you.
Yeah, it would be Earth if you were looking at like the moon or one of the satellites going around the Earth, then you would put the mass of the Earth right there. All right, good. Moving on. Where do I need to go? Where's that? Put that and zoom. Where have you put it? All right, I think this is group 4, right? So you're doing problem 2?
Yeah.
Anybody got an answer yet they want to check?
I'm working on C right now.
Okay, what'd you get for the period?
43,087 seconds.
Yeah, I just rounded it to 4.3 and then I went times 10 to the 4th. That looks good.
Okay.
All right. And there's 2 ways you can do C, right? As I see it. Once you got the period, you can go 2 pi r divided by the period, or you can go the square root of G times the mass over the radius, your choice. I did it both ways just to make sure I didn't make a mistake.
Okay.
All right. Either way is right, though. Other questions? Everybody happy?
Yep.
All right, I'll leave you guys alone.
Pi squared over GM times
Right.
radius cubed.
What's up, guys?
Oh, hi. We just want to confirm for the orbital period, are we using the t square equals 4 pi square over GM r squared?
You could do it that way. I think
Is that-
once you've got the velocity from part
Yeah.
A, you can go either way. Okay, you can either go 2 pi r divided by that velocity,
Oh,
or you can do the 4 pi squared over GM r
yeah.
to the third. Either way, whichever way you want.
Yeah,
I did it
can we
both
just-
ways.
Can we just do the v equals 2 pi r over t?
V is equal to 2 pi r is, yes, absolutely.
That one's
That's probably the
easier.
quickest way. Once you got, what'd you get for your velocity?
5596.98 meters per
Yeah,
second.
I rounded it to 5590, close enough. And so then the easiest way I think to get your answer
Mhm.
is what you said. V is equal to 2 pi r. And am I writing over your stuff? Because I see some.
No,
of your,
you're good.
okay, divided by period. And so period is just 2 pi r, and it's the same r you use to get the period divided by, or to get the velocity. You put it right in there. Okay?
So it's going to be double the Earth's. So that number.
The radius for you is 2 Earth radiuses. Yes.
Okay, thanks.
That's still 2 r radius of the Earth. Yep. All right. See you in a
Thank
bit.
you.
You bet.
Hi, Dr. Chikolsky.
Hey, how you doing? Any questions? You want to check answers? Anything?
Yeah, I wanted see if I'm on the right track for the
Okay.
the period. Um,
Same here.
so when we use the the mass that we're gonna use is, are we using the mass of the gravity, or do we have to find the mass of the satellite and then do it?
No, it's always the mass. Let me share a screen here with you.
Okay.
Okay, so when you're finding the period,
Mm-hmm.
it's the mass of whatever the thing at the center is. And so in this case, I think it's the Earth, right?
Yeah.
And you got the satellite going around. So when you're doing t squared equals 4 pi squared over g m times r cubed, m is the mass of the thing at the center.
Okay.
Okay, and hopefully that's exactly what you did when you found the velocity, right? When you went velocity of g mass over r, right? You should use again the mass of the Earth. The mass is the same mass right there. All right.
Got it.
What'd you get for your velocity?
Well, I found the time period first.
Oh, you're doing period first. Okay. Do you have a number yet? Or you?
Yeah, I got 1.43 times 10 to the 4th.
Perfect. Yep, that's it.
And
now
then I
you
was
got
gonna-
now you okay. So now you got a couple choices on how to get velocity. The quickest way, now that you got that number, might be just to put that period right in there with your radius right there and calculate the velocity that way.
Yeah, I did, and I
You got
got-
choices here. Yeah,
Yeah, I did that, and I just got 5,597.
perfect. You're there.
Okay.
All right, I'm
And-
leaving.
I have a quick question though.
Sure, go ahead.
So the units for the velocity would be meters per second, right?
Yes,
And what would the units be for the period?
time, just seconds.
Just seconds?
Yeah, and then units here are meters, seconds, no units on 2 pi.
Okay.
All right,
Thank you.
you bet.
Thank you.
All right. How do I get out of here? Leave breakout room, that's how.
I keep on delaying it, you know.
Oh, Dr. Tukolsky,
Yeah, I don't know how I
can
came
we
back.
share? Can we share ours?
Sure. Yeah, you
Yay.
have, let's see, okay, yeah, we'll give it a shot. It's about time I break, about 5 minutes left. I'm gonna probably end all the breakout rooms and yeah, you guys can do problem 3.
Is it okay if I just flip my camera to show you the work because
Yeah.
I'm on my phone? Okay.
Yeah, as long as it's, yeah, that might just put it up to your give it a try that way. All right,
Alright.
that way you don't have to upload. All right, Sydney asked for questions. I gotta go join them. All right, Sydney, it says you asked for a question. What you got?
Yes, so we've worked all of our way through the problems
Okay.
for number 2. We were just a little bit confused as to what the units are for both B and C. So we found T and then we're finding velocity, but without the
Yep.
units for T, I can't.
Okay. Period is a time, so it's seconds. Let me share this. Okay, what'd you get for your time? Or what'd you get for your period?
For T, we got 4.92 times 10 to the 12th.
Did you? Yeah, something's up with that. That you're doing problem 2, right? That's a little big. So which way did you do it? Did you go 4 pi squared? That's a squared over G mass r cubed.
Yes.
Okay, what mass did you use right here?
The 6.37 times 10 to the 6th.
That's radius. Mass of the Earth is about 6 times 10 to the 24th kilograms. I think you read the wrong column on the chart.
Yeah, I think I did too.
Yeah, no, I think you read the distance, the radius instead. Okay. Yeah, so that number should be about, it's actually 5.97, I think exactly. A lot of people just round it to 6. This distance here is going to be that number that you just said, 6.37 times 10 to the 6th meters. And then you add on the height of the thing, which is, oh, I got a 2,200, 3 zeros, and then that's kilometers. So be careful right there because that adds another 1,000, right? And so that's what goes in right there. Yeah, it's the units and it's all the funny numbers, I guess, for lack of a better word. All right. So you're gonna have to fix that up and then upload it on Monday.
So we convert that kilometers to meters.
Yeah. Yeah, so because you got to add apples to apples, right? So you got to get this into, so just, all it does is it adds another 3 zeros, right? That's what kilometers does.
Okay, thank you so much.
You bet, no problem. Yeah, it looks like a couple people are back already because you're finished, I guess. Just about everybody back. All right, I think everybody, nope, there's group 2 is still off. Nope, are they back? Yeah, I'm waiting on one group. Yep, one group is still out. Looks like they're back now too. All right, so just these problems, it's more of a, hey, what's the equation? Put the numbers into the equation, grind it out on your calculator, right? The problem though is you've got to know, well, which mass am I talking about? Which radius am I talking about? Am I center to center on the radius? And so those are the things that cause people to get the problem wrong. It's just not knowing exactly what each of the symbols represents. But in terms of complexity, it's not as hard as solving Newton's second law with 2 equations, 2 unknowns, a bunch of algebra. But the numbers are, always 10 to the minus 11th, or a mass of 10 to the 24th, like the Earth's mass, 6 times 10 to the 24th. And so that makes it a little challenging. Anybody want to show or share their answer to problem 1? You know the answer. It's a year, right? How many seconds is that? Anybody from one of the group 1, group 2, or group 3 want to share with the group?
Group 3 can go.
Go ahead, group 3. What you got?
For which problem?
You're doing problem 1, right? You did problem 1.
Never mind.
Never mind. Not gonna do it. All right. Well, the answer is 1 year. The only question is how fast the Earth is moving, and it's moving at about 2.9, almost 3 times 10 to the 4th meters per second. And that's an interesting number in physics. All right, so that's the answer for you guys that you should be shooting for. Group 4, 5, or 6. Anybody want to share their answer?
I have a question about problem 1.
Yeah, go ahead.
So we use the mass of the sun, and then for the radius, do we use the distance from the sun to the Earth?
Yes.
Okay.
Exactly. Yeah.
Okay.
Yeah, and you should get the number of seconds happens to be almost 3.16 times 10 to the 7th seconds, which if you convert to days turns out to be 365 days. All right. Nobody for 2. All right. I know a couple. Some people said the right answer. I forget who it was.
Which part do you want for the?
You can give me both numbers.
I think there's 3 different parts for 2.
Yeah, I guess that's true. The first one is just to get the radius.
Yeah. Well, the period is 43,087 seconds.
Okay.
And the velocity I got was 3,874 meters per second.
All right, that's good. And who's talking right now?
Sean.
And who else is in your group, Sean?
I'm not sure. Whoever was in group 4.
Group 4. All right. Sean, Olivia, and Allison. All right. So you guys don't have to upload. And Olivia. All right. Last set of groups. Groups 7, 8, and 9. I had 9 requested. Go ahead and answer. What do you guys got?
All right, I'll go. So, I don't know how to flip the camera on the phone. Wait. So this is the equation you're using. You're finding the g times the mass of the Earth over the radius, which is 2 times the radius of the Earth.
Okay.
So my answer was, you can round to 5590 meters per second.
Okay.
And then for the period, it's 1,425 seconds about.
I think you're missing a 0 there. Yeah, you
Where?
should check it again. There should be one more zero. It should be 14250.
Oh, I probably just skipped
Yeah.
it. But
Okay.
this is your equation you're using.
Yeah. And for everybody else, sometimes that's the easiest way to get the period. Sometimes the easiest way is use Kepler's third law. Of course, Kepler's third law, you got to cube the radius, you got to multiply by those wacky constants, and then you got to take the square root at the end. So you could do it both ways. My advice is always pick the easiest way. All right. Hey, that's about all I got. I'll be hanging around here for office hours for a little bit. I don't have the 10:30 session on
Back to
Friday,
sleep.
but that's it. Any questions? Somebody's starting to talk there?
Kristen, we can hear you.
Okay. All right. Otherwise, have a great day, great weekend, and we'll see you on Monday.
Dr. Tukolsky, my
Yeah.
group doesn't have to submit it, right?
Yeah, your group, that's
All right.
Nina and
Jackie.
and Jackie. Yep, you guys
Yeah.
don't have to upload. I'm just going to give you
Thank you.
grades right now.
All right, thanks.
All right.
Thank you.
And that's same with Sean, Alice, and Olivia. Yeah, you guys, Olivia, you don't have to submit because you're with Sean, and I assume you guys all checked your numbers. Questions from you two? Hello. Nope, I'm by myself. I'll stop recording then.